So today we are going to discuss about the nature of the chemical bond. So when we talk about the chemical bond, it is the attractive force which holds together constituent particles in this chemical species. So the tendency of atom to form the chemical bond is just to satisfy the stable configuration of 8 electrons in their valence shell. So for example, when we talk about the methane, CH4, there is a force of attraction which is holding the carbon and the hydrogen together just to satisfy their stable configuration. Like carbon is having 4 electrons in its outermost shell, it's sharing this electron with the 4th hydrogen. So in all, if you'll find the outermost shell of the carbon is containing a complete octet to stabilize this, so kind of bond formation between them. So when I talk about the chemical bond, there are different types of the bond formation possible. So first we'll be talking about the ionic bond. Ionic bond is something which is a complete transfer of electron from one element to the other element, creating cations and anions. For example, when we talk about sodium, its atomic number is 11, electronic distribution 1s2, 2s2, 2p6, 3s1. So outermost shell of sodium is containing 1 electron. If it donates it, the remaining configuration, that's a stable configuration of a neon, can be achieved by the sodium. So when it donates that particular electron, Na becomes Na plus with a stable configuration of 1s2, 2s2, 2p6. While in case of chlorine, with the atomic number 17, we have configuration 1s2, 2s2, 2p6, 3s2 and 3p5. So now the outermost shell of chlorine contains total 7 electrons, so it can gain the electron which is donated by the sodium so as to acquire negative charge with the configuration stable 1s2, 2s2, 2p6, 3s2 and 3p6. So now these are the oppositely charged ions, that is cations and anions are formed, and the electrostatic force between them will make the compound NaCl, which is the ionic compound. So in all, ionic bond, it's a complete transfer of electron from one element to the other element, forming a stable configuration. Now, which kind of the element can form this kind of ionic bond? So we have certain factors to decide or to have the ionic bond formation. First of all, ionization enthalpy. In case of ionization enthalpy, it's something the energy required to remove the electron from the outermost shell. So those elements who requires less energy, that is having low IE, will have a tendency to lose electrons easily from the outermost shell. Hence, we are expecting low ionization enthalpy elements will form the ionic bond. For example, the elements from group 1 or group 2, since they contains 1 or 2 electrons in their outermost shell, they can donate these electrons easily. So their ionization enthalpy is low and they can form the ionic bond. Secondly, the elements which are having high electron gain enthalpy. Since their electron gain enthalpy is very high, they can gain electron easily. For example, like chlorine, since they contain 7 electron in the outermost shell, they can gain electron easily, so they also tend to form the ionic bond. For example, mostly the group 17, which is having high electron gain enthalpy. Point number 3, under this we can cover those elements or those compounds having high lattice enthalpy. Higher is the lattice enthalpy, more is the tendency to form the ionic bond. So overall, to form the ionic bond formation, so 3 conditions can be satisfied. One is low ionization enthalpy, high electron gain enthalpy and high lattice enthalpy. The second kind of bond formation that we can discuss is nothing but the covalent bond formation. Covalent bond formation is the sharing of electrons between the atoms. For example, if we talk about the chlorine, chlorine has 2, 8, 7, that is 7 electron in its outermost shell. So this is chlorine having 7 electron in its outermost shell. It can share this 7 electron with the other chlorine. So when they share one pair of electron between each other, for each of this chlorine the octet will be complete, and they can get stabilized. So this kind of sharing of electron between the atoms, we call this bond as the covalent bond. Depending on how many electron pairs have been shared between them, the number of bonds can be formed. For example, if I talk about oxygen, oxygen contains total 6 electrons in its outermost shell. Here oxygen shares 2 electron pair between each other to complete their octet. Hence, the number of bonds present between the oxygen atom are 2. Similarly, in case of nitrogen, 3 electron pairs are shared between the two, and hence now their octet is complete. So therefore, the bonds between present two nitrogen atoms are 3. In case of the ion, that is covalent bond character, before we discuss what kind of the different theories has been put forward for the bond formation, let us now first talk about the different parameters related to the bond formation. So first of all, we are going to talk about the formal charge. When we talk about the formal charge, it is the charge which is present on the atom in the polyatomic molecule. And to calculate this formal charge, we have a formula: number of valence electron in the free state of the atom minus number of non-bonding electrons. That is, in short, we talk about lone pair of electrons plus half into number of bonding electrons which are being shared. Now let's talk about the formal charge on the different oxygen atom. Let's talk about ozone. Ozone has structure. Oxygen is bonded to other oxygen by double bond, and with the other oxygen by the single bond. So here this oxygen, since 2 bonds are satisfied, it contains 2 lone pair. Here 3 are satisfied, so 1 lone pair is utilized, so this is carrying positive charge, and here there are 3 lone pairs. Now let us number this oxygen as 1, 2 and 3. We'll calculate the formal charge for the different oxygen. Let's talk about the first oxygen. For the first oxygen, when we talk about the oxygen, the atomic number of oxygen is 8. So electronic distribution is 2, 6. So all these atoms contains 6 electrons in the valence electrons in their free state. So for the first oxygen, the formal charge will be equals to the number of valence electrons are 6 minus, we need to calculate first of all the number of lone pair present over here. We can see the lone pair of electron on this oxygen are 4 plus half into, we have to calculate number of bonding electrons. Since this oxygen is bonded by double bond, so there are 4 electrons involved in this particular bond. So number of bonding electrons are 4. So this is 6 minus 4, this is plus 2. So it is 0. In case of second oxygen, when we talk, let us talk about its formal charge. So for this oxygen, it is number of valence electrons are 6 minus number of lone pair 2 plus half into, now this oxygen has 3 bonds, so 3 into 2, that is total bonding electrons are 6. So 6 minus 2 plus 3. So this is 6 minus 5, that will be equals to 1. So formal charge on this oxygen is plus 1. While for the third one, formal charge will be equals to number of electrons in its outermost shell 6 minus lone pair are 6 plus half into number of bonding electrons are 2. So this will be total minus 1. So charge on this oxygen will be minus 1. Let us discuss now the polar character of the covalent bonds. Let us talk about molecule like HCl. Now this is something, a bond which is formed by the sharing of one electron between the hydrogen and chlorine. But the electronegativity difference, if we talk about it, the chlorine is more electronegative than the hydrogen. So it will try to pull all the shared electron towards itself. Because now chlorine carries all its electron towards itself, the side of the chlorine will become partially negative and the hydrogen will become partially positive. So due to the difference in the electronegativity, here 2 poles are created. One side of the molecule is partially positive and the other side of the molecule is partially negative. So 2 poles created, hence we call this molecule as polar molecule. So polarity of the bond is the magnitude of electronegativity difference which reflects on its degree of polarity. Now this difference of polarity we can calculate in terms of dipole moment. This dipole moment is defined as it is something the product of the charge or magnitude of the charge into the distance between that particular atoms. So this is something distance of separation. So this is mu is equals to q into d. This particular dipole moment is generally expressed in the unit d, which is d by. This d by is equals to 1 into 10 raised to minus 18 ESU, or it is also measured in the coulometer. 1 d is equals to 3.33564 into 10 raised to minus 30 coulometer. The dipole moment depends on the type of the molecular structure. When you have molecules like diatomic molecules, then for this the dipole moment will be decided by the difference in the electronegativity. Now for example, if you are comparing for the diatomic molecule, let's say for HF, HCl, HBr and HI. So when I talk about from fluorine to iodine, the electronegativity goes on decreasing. So the highest electronegativity is associated with the fluorine. Hence, when it is attached to the hydrogen, the difference in electronegativity is very vast. Since it is having the highest difference of electronegativity, the dipole moment is also highest. But when I talk about the molecules which are polyatomic in nature, for them the dipole moment will be decided by the vector sum of the dipole moments of different atoms. For example, if you have molecule like carbon dioxide, which is linear molecule. Now between these two, if you talk about, oxygen are electronegative, but we are experiencing, that is carbon is experiencing the dipole moment pull from both way equally, and that's why the total dipole moment on this molecule will be equals to 0. But instead of this, if you have a molecule like water, since it is a bench shape, the dipole moments are not cancelling each other completely, and that will create some dipole moment for this particular molecule. So definitely for polyatomic molecules, the dipole moment overall will be dependent on the structure of the molecule. The calculation of the dipole moment will help us to find out whether the molecule is polar or non-polar. For example, when I talk about the molecules like carbon dioxide, since it is in the linear form, the dipole moments are cancelled by each other, and hence the dipole moment will be 0. We can call this molecule as non-polar in nature. But similar type of molecule like SO2, when it is bent in shape, the dipole moment is not cancelled, and hence it is having certain dipole moment, making this molecule polar in nature. So to find out whether the molecule is polar or non-polar, we can calculate the dipole moment. The dipole moment will also depending on the polarity of the molecule, degree of polarity. Greater is the dipole moment, greater is the polarity of the molecule. Also, it will help us to find out the shape. If the molecule is non-polar in nature, that means its dipole moment is almost equals to 0. Definitely that molecule will be symmetrical in nature, symmetrical in shape. And if it is having certain dipole moment, that means the molecule is somewhere unsymmetrical. The dipole moment also help us to calculate the ionic character of the molecule. It has been seen that if the dipole moment difference or electronegativity difference between the two atoms involved in the molecule, if it is equal to 1.7, then particular molecule will have 50% ionic character and 50% covalent character. But if the difference is greater than 1.7, the molecule will be permanently ionic in nature. And if it is less than 7, the molecule will be permanently covalent in nature, having more covalent character over here and having more ionic nature over here. We can also talk about the covalent character of that ionic bond. Some ionic bonds you will find them having little bit covalent character. So according to the Fudgens rule, when the ionic bond will show a covalent character. There are certain rules like the cation size has to be smaller. Secondly, the anion size has to be larger. There should be high charge on cation as well as on the anion, and cation should have 18 electron shells. So if these all conditions are satisfied, the ionic bond will have to some extent the covalent character. Next we're going to talk about the different theories for the bond formation. So we are going to first talk about the valence bond theory. According to the valence bond theory, when the covalent bond is formed between the two atoms, there is overlapping of the atomic orbitals which are containing the unpaired electrons. For example, if there is a s orbital having unpaired electron, it will overlap with another s orbital having the unpaired electron with the opposite spin. When this overlapping will take place, there will be neutralization of the spin and the bond formation will take place between the two atoms. During the course of this overlapping, the potential energy of the system will decrease. As the energy of the system is decreasing, the stability of the molecule will be increasing. So overall, to have a maximum overlap, that is maximum the overlapping between the atomic orbitals, more is the stability of the molecule or the more stable bond is formed. But while taking into the consideration the interaction between the atom, when we talk about atom, there is a positively charged nucleus surrounded by negatively charged electron. When the two atoms like this are approaching each other, there are some forces acting between the two. First of all, between the two positively charged nucleus, there is a force of repulsion. When I talk about between the two negatively charged electron, there is also force of repulsion. But between the electron and positively charged nucleus, there is a force of attraction. To have a stable bond formation, always remember the force of attraction has to be more than the force of repulsion. If this condition is satisfied, then only the stable bond formation is possible. Though we say according to the valence bond theory, there has to be the maximum overlap between the atomic orbitals so as to get a stronger bond, but there is certain limit of overlapping, because if this particular distance is crossed, then the nucleus of the two atoms may come closer to each other and that will start giving a more force of repulsion. So maximum overlapping is possible, but up to the certain distance, beyond that the force of repulsion starts acting. In the case of valence bond theory, the overlapping takes place between the two orbitals having nearby energy. Therefore, this is the one kind of overlap we have presented over here. It is called as SS overlap. Even the p orbital can overlap with each other. P orbitals generally have the double shape. So when the p and p actually overlap with each other, we are going to get the formation of pp overlap. Since S and P, they have energies nearby to each other, so SP overlap is also possible, giving the bond formation of SP overlap. So valence bond theory can explain different bond formation between the molecules, but there are certain limitations. According to valence bond theory, the number of unpaired electrons is equals to the number of bond formation take place. Because of this reason, if I talk about the element like boron with the atomic number 5, we have electronic configuration 1s2, 2s2, 2p1. So in this case, if you arrange the outermost shell electron, the 2s electrons are paired 1, while the 2p we have one unpaired electron over here. So according to valence bond theory, boron can form only compound with the one valency. But in the nature, we have certain compounds of boron like BF3, where the boron has a 3 valency, which is not being explained by the valence bond theory. Also, if I talk about the carbon with the atomic number 6, we have a configuration 1s2, 2s2, 2p2. 2s electrons are paired 1, 2p we have 2 unpaired electrons. So according to theory, carbon can form only 2 chemical bond, but we have in the nature compound of carbon which are tetravalent in nature. So here The valence bond theory is not giving us idea about the exact valency of the element. Also, when you talk about the water molecule, it is HOH. The angle expected according to the valence bond theory to be 90 degrees Celsius. But the actual angle between the water molecule is 104 degrees. And why there is a distortion in the bond angle was not explained by the valence bond theory. To explain all this concept, we need a next theory called as the hybridization theory. The next bond theory concept is the hybridization, which is one of the important concepts to explain different type of bond formation. Let us talk about the carbon. According to valence bond theory, carbon can form only two covalent bond, but in the nature we have a compound of the carbon like methane, where the carbon is tetravalent in nature. The explanation for this has been given by the hybridization theory. In case of carbon, the atomic number is 6, so configuration is 1s2, 2s2, 2p2. So in its ground state, outermost shell, the 2s electrons are paired 1, and the 2p electron, we have 2 unpaired electron. But since the valency of the carbon is 4, one of the important step which is involved in hybridization is excited state. In excited state, one of the electron from the 2s absorbs the energy and it goes to the vacant orbital of 2p. The energy required for this excitation can be taken during the formation of bond. When the hydrogen atom approaches the carbon, there is some liberation of energy, and that is being utilized by the carbon for the excitation of electron from 2s to 2p. So now carbon has 4 unpaired electron and it can form these 4 bonds. But the problem is, since one of its electron is in s orbital and the remaining are in p orbital, carbon will form the 4 bonds but not with the equivalent energy. When you analyze the structure of the methane, you will find all 4 bonds of the carbon are equivalent. To generate this equivalent bonds, it has been said that the 4 electrons, unpaired electrons of the carbon undergoes the hybridization process, which is a mixing of the orbital. So one orbital s and the 3 p orbitals are mixed. That's why this hybridization is called as the sp3 hybridization. So it is mixing of orbital and forming 4 new orbital. We call them as sp3 hybrid orbitals. These sp3 hybrid orbitals now will have the equivalent energy, and hence when the carbon now forms the bond, it will form the bond with the equivalent energy with the 4 hydrogen atoms. So now this is a carbon having the 4 sp3 hybrid orbital, and these sp3 hybrid orbital will be having unpaired electron each. Since there is a repulsion between the bond pair and bond pair, these electrons will try to go maximum away from each other, forming a tetrahedral structure. When they overlap with the s orbital of the 4 hydrogen, you will get a geometry of the methane which is tetrahedral. So it is in short the carbon in the center and the 4 hydrogen at the corners of the tetrahedra, giving a tetrahedral geometry with a bond angle of 109.5 degree. Similarly, we can talk about the next molecule, that is BF3. In case of boron, the atomic number is 5, configuration 1s2, 2s2, 2p1. So outermost shell of 2s containing pair electron and the p containing a single electron. But since the valency of boron is 3, there is an excited state in which one of the electron from the 2s will be excited to 2p, generating 3 unpaired electron. They undergo hybridization. Now since there is a mixing of 1s and 2p orbital, this hybridization is called as sp2 hybridization, in which we have 3 newly generated orbitals. Since they will try to go away from each other, they will have a trigonal planar structure that will be overlapping with the 3 fluorine atom. So the geometry of molecule will be boron in the center, 3 fluorine at the corners of the trigonal planar structure with the bond angle of 120 degree. When I have sp hybridization, since there are 2 orbitals involved, they will try to go maximum away from each other, giving the angle of 180 degree. So overall, we can have different type of hybridization depending on which kind of orbitals are mixed. Let us say if we have a mixing of S and P, it is sp hybridization with the bond angle of 180 giving linear geometry. So it is something, the central atom having two orbitals forming a bond between two atoms. If I have one S and 2p orbital mixed, it is sp2 hybridization with the bond angle of 120. The geometry is trigonal planar, in which central atom is bonded to the 3 atom in the trigonal planar fashion. When we have 1s and 3p orbital mixed, then we have sp3 hybridization with the bond angle of 109 giving tetrahedral geometry, in which the central atom is bonded to 4 atoms which are present at the apex of the tetrahedra. If it is 1d orbital, 1s orbital and the 2p orbitals are mixed, it is dsp2 hybridization with the bond angle of 90 degree, which we call it as a square planar structure, in which there is a central atom bonded to 4 different atoms. They are arranged in the 4 corners of the square, so it's a planar structure. We can also have the hybridization in which 1s, 3p and 1d giving sp3d hybridization with the bond angle. Now here we call this as trigonal bipyramidal structure, in which the central atom bonded to 3 atoms in which they are in one plane. It's a trigonal form. One is above the plane, one is below the plane. We can also have 1s, 3p and 2d combination. So it is sp3d2 called as octahedral geometry, in which the central atom bonded to 4 atoms forming a base of square. One is above the plane, one is below the plane. And finally, so if 1s, 3p and 3d orbitals are mixed together, giving the hybridization of sp3d3, which will be having pentagonal bipyramidal structure. So in the pentagonal bipyramidal structure, the central atom will be surrounded by 5 different atoms in the pentagon in one plane. One atom will be above the plane and one atom will be below the plane. So these are the different hybridization possible with the mixing and recasting of the orbitals. But in the case of next theory, it says that it is valence shell electron pair repulsion theory. So it is VSEPR theory, which says that when we talk about the particular element, let us talk about molecule like ammonia. In case of ammonia, the nitrogen is having the atomic number of 7. So electronic distribution is 1s2, 2s2, 2p3. So the 2s electrons are the paired one and the 2p unpaired electrons are there. Now here there won't be any excited state because now we have 3 unpaired electrons and the 3 valency of hydrogen. In this case, they will undergo sp3 hybridization, which will generate 4 new orbitals with one lone pair. Since there is a presence of one lone pair on the nitrogen and the remaining are the 3 orbitals with single pair, there is a repulsion between the lone pair and the bond pair. And this repulsion causes the distortion in the molecule, where the 3 hydrogen, now when it will be bonded to that particular nitrogen will be in the center and the hydrogen will be at the base of the pyramid type of shape. So usually we are expecting for the sp3 hybridization the tetrahedral geometry, but now it is being distorted to the pyramidal geometry with the bond angle of 107 degree. So whenever there is a presence of the lone pair, that always causes the distortion in the molecule. So what kind of distorted molecules we can have due to the presence of that particular presence of the lone pair? Let us talk about it. When you talk about, let us talk about first sp2 hybridization. In sp2 hybridization, just we have discussed, as the 3 orbitals that are there, 3 atoms are there, they migrate or they are present at the apex of the trigonal planar structure. But if I say there is sp2 hybridization with one lone pair, then there is a lone pair at this point which will now give the geometry that bend shape. But if I say there are two lone pair, since now there are two lone pair present over here, the molecule geometry will be just linear. So presence of the lone pair will cause the distortion in the molecule. Previously the molecule was trigonal planar, which is changing to bend shape, and now it is linear. When I talk about sp3 hybridization, the standard geometry of the molecule is tetrahedral in form. But if we have, let's say, one lone pair, the one lone pair will cause the geometry to be distorted. This is lone pair. Now only 3 atoms are left that will be present in the that is at the base of the pyramidal shape. So because of one lone pair, the geometry has been distorted to the pyramid. If you have two lone pair present, this is one lone pair, this is another lone pair. So now only 2 atoms are left over here, that is giving the geometry which is bend shape. But if we have 3 lone pair present, so this is central atom with 3 lone pair, so definitely now the molecule will be linear in the form. When we have sp3 dehybridization, we are expecting the geometry has to be trigonal planar. One atom above and one atom below, so this is trigonal bipyramidal shape. When you have one lone pair over here, since it is one lone pair present at this point, the geometry will be distorted to seesaw shape. Then if you have two lone pair present over here, so these are the two lone pair present at this point, now the geometry will be distorted to T-shaped. If we have 3 lone pair present at this point, the geometry will be distorted to bend shape. So every time due to the presence of the lone pair, there is a distortion in the molecule. Let us also talk about the next hybridization, that is sp3 d2 hybridization. In sp3 d2 hybridization, we are expecting there is a central atom surrounded by 4 atoms in one plane. One atom is above the plane and one atom is below the plane. Due to presence of one lone pair, since now let's say one lone pair is present, now 4 atoms still in one plane, it's a square, but only one atom above, so this is square pyramidal shape. And if I have 2 lone pair present, this is also lone pair, this is also lone pair, so now the geometry will be distorted to square planar shape. So these are the different distortions in the molecule. But if the MCQ point of view, any question comes related to this, then how to solve the question to find out the exact geometry of the molecule. So in that case, when MCQ comes related to the finding geometry of the molecule or finding hybridization of the molecule, we'll follow one simple formula. We'll first calculate the number of hybrid orbitals for the central atom in the given molecule. So the number of hybrid orbitals will be equals to half into number of valence electrons involved plus number of monovalent atoms plus whatever is the charge on the anion if it is anionic molecule, and you have to subtract the charge on the cation if it is cationic molecule. This is simple formula we'll use in order to find out the hybridization. So let us solve some examples based related to that. For example, if you are doing calculation for methane. Now in the methane, to find out the number of hybrid orbitals, first of all, this is half. In the valence shell of the carbon, there are 4 electrons present. So the number of valence electrons are 4 plus hydrogen is a monovalent atom. So I will add 4 over here. It's a neutral molecule. So it's not an anion, it's not a cation. So charge on the anion 0, charge on the cation is 0. So total is 8 divided by 2. The answer is 4. Now check whether the number of hybrid orbitals is matching with the number of atoms or not. If it is matching, there is no lone pair. So it is simple 4 hybrid orbital. Definitely it's a sp3 hybridization with no lone pair, and that's why we are expecting the geometry of the molecule has to be tetrahedral. But if I talk about the molecule like ammonia, hybrid orbitals will be equals to half. The outermost shell of nitrogen contains 5 electrons, plus there are 3 monovalent atoms. It's a neutral molecule, so plus 0 minus 0. This is 8 divided by 2, so answer will be 4. But this time the number of hybrid orbitals are more than the number of atoms which are bonded to the nitrogen. How many more? So it's 1. That's why this is sp3 hybridization with 1 lone pair. Due to the 1 lone pair, there will be distortion in the molecule. Now tetrahedral geometry will be distorted to the pyramidal shape. So in this way you can calculate for any molecule. Let us say we are calculating for XeOF2. I need to find the hybridization and the geometry of this molecule. So I will calculate for Xe. So hybrid orbitals will be equals to, xenon is the noble gas and hence number of electron in the valence shell are 8 plus monovalent atoms. Now oxygen is a divalent, so I will calculate for the fluorine only. Fluorine is a monovalent, so I will add 2 into this. It's a neutral molecule, so plus 0 minus 0. This is 8 plus 2, that is 10 divided by 2, that will be equals to 5. But number of bonded atoms to the xenon are 3. So we have 5 hybrid orbital, but only 3 bonding is taking place. 5 hybrid orbitals, that means sp3 dehybridization, but only 3 bondings are there. That's why it is with 2 lone pair. When I have sp3 dehybridization, the geometry is trigonal bipyramidal. With 1 lone pair, it becomes seesaw, and with 2 lone pair, it becomes T-shaped molecule. So in this way, with this formula, we can calculate the number of hybrid orbitals for the different molecules, and also we can find out the geometry of the molecules. In the next part, we'll be talking about the molecular orbital theory. In case of molecular orbital theory, it is the molecular orbitals which are formed by the combination of the atomic orbitals on the proper symmetry and comparable energy. The number of molecular orbitals which are formed, it is equals to the number of orbitals which are combining. Let us say if I am combining 1s orbital of the 2 atoms, then when the 2 atomic orbitals will combine, I will get formation of 2 molecular orbitals. One molecular orbital which is having lower energy than the atomic orbital, that we call it as bonding molecular orbital. And the other orbital which is formed by the combination having higher energy than the atomic orbitals, that's called as anti-bonding molecular orbital. Now this is being formed by the 1s orbital, and s orbital always overlap actually, so I will call this as sigma bond, sigma 1s orbital. While this is anti-bonding, so I will use sigma star 1s orbital. So there are 2 orbitals formed due to the combination of 2 atomic orbitals. Now in case of the 2s will also combine, since it's actual overlap only. So we are going to get sigma 2s and sigma star 2s. When I talk about the 2p, we have 3 different orbitals. Let us talk about the helium with the atomic number 2. Now, if the helium forms a bond between the other helium, let us confirm it. What bond order will be there between the two molecules? Now, there is atomic number 2 plus 2. There are 4 electrons to be distributed. So, we can write a configuration sigma 1s having capacity of 2 and sigma star 1s having capacity of 2. Now, bond order is equals to number of bonding minus number of antibonding electrons divided by 2. So bonding electrons over here are 2, antibonding are 2, so that will be equals to 0. So there is 0 bond order, that's indicating 2 helium cannot form bond with each other. In case of, let us take one more example, we'll take example of C2. We have to find the bond order between the two carbon atom. Every carbon atom has the atomic number of 6. So it is 6 plus 6. We have to distribute total 12 electrons. So let us distribute. We have sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So up till now we have completed 8 electrons. Now 4 more to go. So we'll fill electrons in the next pi 2px2 and pi 2py2. Now total 12 electrons are filled over here. We can see bonding electrons are 2, 2, 2 and 2. There are total 8 electrons which are bonding. Minus there are total 4 electrons which are anti-bonding. So this is 4 divided by 2, that is equals to 2. So 2 carbon atoms can be bonded to each other by 2 bonds, that is double bond between each other. Since all electrons are paired over here, we can say the molecule is diamagnetic in nature. Let us take one more example of the molecule oxygen. One oxygen is 8 electrons. So 2 oxygen total 16 electrons to be filled. Now here we'll start with 1s sigma, that is 2, sigma star 1s, that is 2. We have filled here 4 electrons. Then we have sigma 2s2 and sigma star 2s2, another 4 electrons. So till now we have completed 8 electrons. Now we have next, that is sigma 2pz2, then pi 2px2 and pi 2py2. So 4, 12 and 2, that is total we have completed 14 electrons. Now in case of remaining 2 electrons, we have pi star 2px and the pi star 2py. Since they are at the same energy level, the Hund's rule says that the pairing will not take place until and unless every orbital of the same energy will be filled with 1 electron. So here we'll be having 1 electron in each orbital. So when you write the electronic configuration over here, we can see there are unpaired electrons present in the oxygen molecule. So oxygen molecule is paramagnetic in nature. If I have to calculate the bond order between the two, we have bonding electrons 2 plus 2 4 plus 2 8 6 plus 2 8 plus 2, that is 10. So 10 bonding electrons are there, minus if I have to calculate the antibonding electrons 2 2 and 2, that is total 6 divided by 2. So it is 4 divided by 2. So answer is 2. So between the two oxygen there is double bond present. So we can use this molecular orbital concept in order to find out whether the molecule is diamagnetic, paramagnetic, and what is the bond order present in it.